Hi, it's Kate, and this is the fourth video for week 1 of Math 23B. Sorry, I've already lost count. But in this video, we're going to talk a little bit about some of the applications of integration because these integrals that we'll discuss come up a great deal in physics and probability, and you'll be doing some examples with them in your small group problems as well as on your problem set this week. So the first one is that you're given a body that occupies a region, as in like a solid form, and you're told that it has a density that is variable. And the density varies depending on the location that you're in that form. And that density function is called mu of x, right? It changes depending on where in the body you're talking about. And so if you wanted to compute the total mass of this body, you would integrate that density function over whatever the boundaries of that region, A, that the body occupies is. And by computing this integral, you would get the total mass. You can definitely think of this as density times. Note that if we have like dx by dy by dz, that's like an infinitesimally small increment of volume. So multiplying these two together, it would not be a surprise that you would be able to compute the mass by integrating this over the entire region. Now, if you were looking for the center of mass of this particular body, now the center of mass is a location, right? Usually the center of mass, in the notation that Hubbard uses, he uses this. I tried to boldface that x as much as I could. So it's x bar. That's the point that is the center of mass. And so he writes x bar as a point that has the following components. And I'm doing an example in R3, though perhaps you'll have an example in R4. But for most of the examples that you'll be working, you'll be dealing with x, y, and z, or x1, x2, x3. And so the way to compute each of these components in the point that indicates the center of mass, you'll have to do that separately. What you're going to do is you're going to compute the integral of x1 right here times the density function and integrate that over the bounds that describe the region A, and then you want to divide by the mass. So generally you want to do this in two pieces. You'll have to compute this integral down here in the denominator first, and then compute the integral that's in the numerator second. Note that unlike that product rule, there's no quotient rule for integrals, so compute these separate from each other, and that's how you'll go about finding the first component. Then you'll do the same thing for the second component. For instance, if you want the y coordinate for a center of mass, you'll do y times the density function and then divide by the mass, or z times the density function divided by the mass for the z coordinate. And so once you've done these three integrals and the mass integral, you'll take the quotient of those three pairs and find each of the components that make up the center of mass. We can also compute the moment of inertia about the x-axis when we're looking at some sort of solid that is perhaps sitting right on the x-axis. We're basically computing y squared plus z squared, which is going to give you, that's r right there, r squared. We're integrating that times the density function across the entire region A. So you're taking the density function, you're multiplying it by the square of the distance from a particular axis. And in a physical sense, what this actually tells you is it helps you determine the torque you need for a particular angular acceleration around this axis. That's way more detail than you care to have in this particular class. We're not a physics class, but it is important to sort of prime that in your mind. You may be running into this in Physics 15 if you're taking that course as well, or 16. There are also products of inertia similar to this. Note that with moments of inertia, if you wanted the moment of inertia around the y-axis, note that you would integrate x squared plus z squared times the density function. Or on the z-axis, that the square of that distance would be x squared plus y squared times the density function. And similar with products of inertia, note that we have xy, we have yz, we have xz. So there are three products of inertia, and you can compute them like so. Products of inertia are a little bit trickier of a concept to think about, but products of inertia are calculations that essentially measure the amount of symmetry of a particular body that occupies the region A with a density function mu. And so what ends up happening is that if you have a body that has a plane of symmetry, as in if you look at the xy plane cleanly slices that particular body in half, that what's above the xy plane and what's below the xy plane are exactly equal, you'll find that the yz and the xz products of inertia are both going to be 0. So what ends up being an interesting result is that when you're dealing with volumes of revolution, right, you take a curve and you revolve it around a particular axis. This was unintentionally a volume of revolution, but any volume of revolution is actually going to be symmetric about two different planes, right? There's going to be the one that sort of slices it through here, and then there's going to be one that slices it vertically through there. So what's really interesting is that, remember, if you have a plane that is a plane of symmetry, the other two products of inertia will be 0. If you have a volume of revolution, that means you have two planes of symmetry. And so what's going to end up happening is that all three products of inertia will be 0. Again, this is outside the scope of what we'll be discussing in the class, but this is pretty cool stuff that you can deduce by calculating a simple integral. The next application is something that many of you have perhaps run into already, having maybe taken AP statistics or any sort of statistics course in the past, but probability theory is a place where integrals play a very critical role. Now, note in probability theory, we have a sample space, S, which consists of all possible outcomes of an experiment. An experiment could be a roll of a pair of dice, a flip of a coin, or here's a great, throwing a dart. So an event A is a subset of S, like a particular outcome for that experiment. In this case, where we're talking about throwing a dart, maybe hitting a bullseye or hitting the region of the board worth 15 points, those two are events. Maybe rolling 2 6s is an event when you're rolling a pair of dice. Flipping a coin and getting heads, that's an event when you're talking about the sample space of coin flips. And so when we're talking about random variables, a random variable is a function that maps from the sample space to real numbers. It assigns a real number to the outcome of a particular experiment. So when we're trying to figure out the likelihood of a particular outcome for our experiment, we have this function that's called a probability density function. And it basically allows us to compute an integral that says, okay, if you want to know what the likelihood is that the outcome of an experiment will result in a value between A and B, you'll take that probability density function, you'll integrate it from A to B, and it will give you that probability. Now, there are lots of different probability density functions. They really depend on the random variable and the behavior of that random variable. Note that there are discrete random variables like coin flips and rolls of a pair of dice, and then there are continuous random variables. I say discrete because the set of outcomes, there's a finite number of them, and you can roll a 3 or you can roll a 4. You can't roll 3.5. Similarly, there are continuous random variables, which is like the height of a human. Say you're going out and measuring people. That means that, if you're looking at the interval of possible height values that's on the scale of real numbers, there are an infinite number of possibilities, and all of those are achievable, right? You could find someone who's 5'7". You could find someone who's 5'7.00000000001 inches. You'd need a really good measuring system, but those are possible outcomes for your random variable. So that's the difference between a discrete random variable and a continuous random variable. And in this particular case, we're talking about continuous random variables here when we're talking about probability density functions. And so when you took a statistics class, if you've taken a statistics class in the past and you're told, okay, this is a random variable that has a normal probability density function, and usually you are asked, okay, what's the likelihood that this random variable will assume a particular range of values? And you flipped to the front or back of your book, and there were a whole bunch of values in a table. That's what the table was actually telling you. It was telling you what these integrals were. Usually the integral was from negative infinity to whatever value you cared about, so you had to figure out what's the integral from negative infinity to A, what's the integral from negative infinity to B, and then subtract the two, one from the other, so that you could find the integral from A to B. If that sounds familiar, amazing. If it doesn't, that is okay. The idea is that you understand that the probability of a particular event happening, in this case our event is we want our random variable to take on a range of values. That means that we can integrate the probability density function over that range, and we'll get the appropriate probability measure. Note that what's really interesting is that if you have a continuous random variable, the likelihood that that random variable will take on a specific value is actually 0, right? If you're thinking about a probability density function, it looks something like this. When you're asking yourself, what's the likelihood it takes on a very specific value, say something right over here, note that we need a range of values in order for us to compute the probability. This is my probability density function. I want to take the integral of the endpoints of my interval. But if I'm asking about a particular value, saying that the random variable takes on the value 0.5 or something like that here, that would mean that I'm no longer discussing an interval. I'm saying that my endpoints would be the same. I only care about whether that random variable takes on a value of 0.5, which would mean that A and B are both 0.5, but we know that from the properties of integration, if the beginning and end of your interval are the same, this is going to evaluate to 0. So the probability of a continuous random variable assuming a particular value is actually 0. With continuous random variables, we only can determine the probability that the random variable will take on a value within a range of values. So you need a starting point and an ending point for that range in order to compute what the probability is of that event happening. Note that there's also a generalization of this. Maybe you have n random variables and you want to evaluate the probability that they will each land within a range, and so you'll describe that range here. Here's the probability density function for each of those random variables. Note that the only difference really is that here we had a single variable. Here we have multiple components in that x value. And so you'll integrate that probability density function again, and here this will be a multiple integral. Note that this is a notational choice unique to the Hubbard textbook, saying orientation does not matter. And so what you'll be doing is however many n components x has, that's how many dx1, dx2, dx3 you'll have. And these will be the particular intervals that you care about for x1, x2, and x3, the various random variables that you're dealing with. If you care about computing the expectation of a random variable, which means that if you run this experiment a great number of times, you have a random variable and you run the experiment a huge number of times, what seems like the average of these outcomes will be. The way that you compute that is you take the random variable that you care about, whatever you're interested in computing the expectation of, multiply it by the probability density function, and then integrate it over the entire sample space. So we'll be doing several examples of that. Usually the random variable we will have will be a number generator that spits out a number between 0 and 1. And so in that case, our sample space are all the real numbers from 0 to 1, and so the bounds of our integral there would be 0 to 1. You'll be given a probability density function right here. More often than not, that probability density function will be equal to 1, which means that no particular interval is being privileged over another. So there's like an equal likelihood that it will end up anywhere on the interval. That's when that equals 1. And most of the problems that we'll be giving you will have a nice probability density function of 1. So what you'll really be doing is integrating the random variable whose expectation you're trying to calculate over the entire sample space. And that will give you the expectation. And again, expectation is if I ran this experiment a great number of times, what would the average of the outcomes start to approach?